Hello friends, welcome to this session. Today we are discussing on phase space and Stirling's formula. Stirling's formula or approximation is used for very large number of n. For the calculation of very large n becomes very troublesome. So with the help of this approximation we can use or we can calculate the bolts FD statistics, B statistics and MB statistics. So in this session, initially we are starting the phase space. We are very familiar that a point in a space has a certain position and choosing origin and axis. Its coordinates can be specified. Such space is called as coordinate space. In this space, corresponding to each set of coordinates, say x, y, z, or position vector r, there exists a definite point r, x, y, z, and corresponding to each point, say r, in this space, there exists set of coordinates x, y, z, or position vector r. In classical mechanics, the state of system of particles at any given time is completely specified by the knowledge of position and momentum, or we can say velocity, of each of its particles. The instantaneous position of a single particle is determined by three independent coordinates, as we already discussed, x, y, z, and the instantaneous motion of a particle is described by velocity components vx, vy, vz, or px, py, pz, or more conveniently by momentum components we are referring as a px, py, pz. Therefore, the state of single particle is then completely specified by position coordinates x, y, z, and momentum components px, py, pz. As purely mathematical concept, we may imagine six-dimensional space in which dx, dy, dz, dpx, dpy, dpz is an element of volume, and the position of space in which dx, dy, dz, dx, dpy, dpz as a point particle. In this space will be described by a set of six coordinates x, y, z, px, py, pz. This six-dimensional space for a single particle is termed as a phase space and a particularly referred as a mu space. So initially phase space, what is the phase space? In this space, corresponding to each set of coordinates, say x, y, z, or position vector r, here the coordinate space, the x, y, z axis are there, the component small x, y, z are there, and position vector small r referred as a capital R. Similarly, one can think of a momentum of space in which axis may be designed by px, py, pz, where px means the component of x component of momentum p and so on. In this space, a point say capital R will be represent the component px, py, pz, or the momentum vector corresponding each set of momentum. One can easily extend it such imagination. Imagine that a space is represented by six axes x, y, z, pxy, py, and pz, and a point in this space has a coordinates x, y, z, px, py, pz. Thus, a point in such a space is representing position as well as momentum and is called as a phase space. Phase of the motion of a particle, that is motion and momentum of particle, can be described or can be represented by a point in the phase space. A point in the phase space which represents the position and momentum of particle is called phase point, corresponding to the particle and each set of momentum. Component or momentum vector P, there exists a point in this space, and these are the imaginary x, y, z, px, py, pz and ps, and a point in the space has a coordinate x, y, z, px, py, pz. Thus, a point in such a space represents position as well as a momentum is called phase space. Another term, when we are considering the phase space, the term is the representing as a point, that is a classical representation. A point representation is there. In quantum mechanical representation, the minimum area will be considered. So this is the representation of the coordinates by classical representation and quantum representation. The phase cells. The phase space can be divided into large number of cells, each of volume having del x, del y, del z, delta px, delta py and delta pz. Such cells are called phase cells. In classical or Maxwell-Boltzmann statistics, there is no restriction on the size. That is, volume of the phase cell may be very small, tending to 0 also. In quantum statistics, the volume of the phase cell R is equal to delta x, delta y, delta z, delta px, delta py, delta pz is equal to h cube. So this is the uncertainty principle by using Heisenberg uncertainty. So here h is the Planck's constant. Classically, a particle can be defined at position x and defined at momentum px, and hence in two-dimensional phase space, the state is represented by a point. Hence, in a phase space, the state can be represented by a point, but it will be represented by an area whose minimum value will be h. If the system consists of large number of particles, such that the state of system is represented by f independent position coordinates, q1, q2, q3 and q up so qf and so on, and f momentum coordinates p1, p2, p1, p2, p3 and so on to up to pf, then mathematically these 2f combined position momentum coordinates may be allowed to define 2f dimensional space, in which the configuration of system is represented by 2f coordinates. So q1, q2, q3 and so up to qf, p1, p2, p3 up to pf. This 2f dimensional space is called the phase space or mu space. The mu space is considered as to be a conceptual Euclidean space having 2f rectangular axis and element of volume. In this space is represented by dq1, dq2, dqf, dp1, dp2 up to dpf. The mu space may be considered as a superposition of mu space. Clearly, the dimension of phase space depend upon the number of degrees of freedom of the system. The instantaneous state of particle in a phase space is represented by a position, that is a point, called the phase point or representative point. The number of phase points per unit volume is called phase density of these points, an element of an volume in a phase space is called a cell. A cell may contain a large number of these points. Quantum mechanically, there is an uncertainty. According to Heisenberg uncertainty principle, we have del px greater than del x equal to greater than h. So this is the quantum mechanically represented by phase space. Now we are discussing the Stirling's formula. For very large number of n molecules, the calculation of n becomes very troublesome. It's very hard to calculate the n position of the molecules. For that purpose, the Stirling's derived the approximation. Stirling used the suitable analytical approximation for log n for large values of n. Here we note that suppose n factorial is equal to n into n minus 1 into n minus 2 up to some 4 into 3 into 2 into 1 factorial. Thus log n, for calculation of the log n factorial n, log n plus log n minus 1 plus log n minus 2 plus up to log 4 plus log 3 log 2 plus log 1. So this is the equation referred as equation number 1. Since log 1 is equal to 0, let us now plot the log x versus x values of x is equal to 2, 3 and so on as a n. So in the figure we are describing the nature of x versus log x. Here the stepper points for each slope of each value having y is equal to log x. So this value is merged here after that. So after that we cannot calculate the value of log. So the area under the stepped curve is summation of n to x is equal to 2. Log x is equal to log of n factorial. For large values of x, the stepped curve and the smooth curve of log x becomes indistinguishable. So we can approximate the log n factorial by integration of log x for x is equal to 1 to n. This approximation is quite satisfactory for large values of n, since log x in the range of large values of x varies only slightly when x is increased by unity. Thus for large values of n, here the log n factorial is equal to integration 1 to n log x dx. So take the integration log x of 1 to n minus 1 to integration of 1 to n 1 by x dx. So x log x n 1 to n minus x 1 to n, we get n log n minus n plus 1. As n is very large, we may neglect the 1 in the above result. So we get log n factorial is equal to n log n minus n. Wherever there is a n factorial, log of n factorial, we can substitute n log n minus n. So this is the Stirling's equation, or this is the Stirling's approximation for calculation of very large number of molecules when they merge. So this equation is referred as a Stirling's approximation. I hope you can better understand this concept of phase space, phase cells and Stirling's formula. Thank you. In the next section we discuss the Maxwell's Boltzmann distribution and statistics. Thank you very much.